package solution that is programmable and can scale to take advantage of market opportunities. Stratix 10MX will integrate a 4 HBM2 stack with a 1 gigabit monolithic FPGA fabric, providing 256 gigabytes per second bandwidth each, 10x higher relative to discrete DRAM solutions at much lower power. Intel's embedded multi-die interconnect bridge will enable ultra-high-density interconnect between the FPGA and HBM2, all resulting in up to 1 terabyte per second of aggregate memory bandwidth. Stratix 10MX has the memory bandwidth and flexibility you need to meet your design targets and get to market sooner across a range of demanding applications. Visit Altera.com/standard.
Hi, this is Bill Jenkins, and I'm going to go over the what's new features in Altera's SDK for OpenCL in version 16.0. What we're focusing on in 2016 is providing power user capability to OpenCL programmers to allow not only control but visibility into what's being created. The SDK for OpenCL produces an optimized solution for an FPGA accelerator. But part of that solution are individual kernel functions that can also be optimized, and the control of that optimization we'd like to be able to provide to our users. And we're providing specific feedback, actionable feedback, in the form of dynamic profiling, enhanced reporting, and also visualization of the outputs. And then through that, we'll provide a set of user-controlled features like attributes, fragments, or constraints to drive how that optimization for those functions get implemented. Also, we support not only OpenCL libraries, but RTL libraries to allow people to optimize kernel functions and then use them later in a traditional software environment. And the final piece are debug tools, not only enhancing our capabilities for emulator, but also integration into third-party tools at Intel and Microsoft. One area that people spend most of their time optimizing are for memory accesses. Knowing that the FPGA has over 8 terabytes per second of on-die memory bandwidth, it's important to tightly couple operations to this local memory. Since these memories are very configurable, rather than building a contiguous memory architecture, the memories can be treated as individual banks, allowing for parallel access to the memory addresses, which means more loads and stores are possible in one cycle. This obviously depends on your memory access patterns, but it's highly beneficial. By using the constraints for declaration of the 8x4 array, these examples show creating 8 banks of 16 bytes wide and 4 banks of 32 bytes wide. Then, by how they are indexed in the code, you can then access multiple rows or multiple columns in parallel. There are a list of all these new constraints in the new documentation. Given that you now have the ability to create these optimized memory architectures, it's beneficial to visually see exactly what is being created by running this local memory visualizer tool. This will show you the loads and stores for each iteration of the loops and how they are accessed internal and external memory. To run the visualizer, simply run the AOCL viz on the object file that gets created from a compile with the -G enabled. Since tasks have been deprecated from the OpenCL spec, and oftentimes running a kernel function as a task allows our compiler to get better quality of results, we are introducing the max global work dimension of 0 kernel attribute that will remove all the unnecessary hardware that gets generated within NG-range kernels for work items. This way, the kernel will not use any global, local, or group IDs, and guarantees that the kernel will be queued as a task. Another new kernel attribute is the auto device and queue attribute that removes all the unnecessary hardware for the host communication to enqueue each kernel individually. This is extremely helpful in creating many instantiations of optimized task kernels, such as a systolic array. It would simply take far too long for the host to enqueue each kernel individually, so this tells the compiler the kernels will start running on their own. This is extremely useful in packet processing or image processing applications. Thinking of how we can tie these two last features together to build very optimized architectures in the FPGA, you first want to design a very efficient optimized task-based kernel function. Now, how do you scale that up to dozens or even hundreds of implementations of that kernel? That is where this new attribute, known compute units, can be used to specify a 1- or 2-dimensional array of these task-based kernels. We are also providing the API to identify any specific kernel in the array with a getComputeID function. Think of this as an ND range of tasks and allowing you to address each processing element individually in case you wanted to treat the edge pixels differently than the sensor ones, for example. Now, using channels or pipes, we can easily define the topology of data movement between the processing elements using software constructs and quickly create specific architectures for leveraging the result reuse from each processing element and keeping the data on the FPGA without needing to go to external memory. The largest area of improvement for the 16.0 SDK is in providing much more useful detail. For example, where in the code there are inefficiencies and how to improve the performance by removing those inefficiencies and making changes. It will even tell you where in the documentation to read and learn how to optimize the code for that particular coding style. The reports are providing this information much earlier and prior to building the whole FPGA, which means faster feedback to more iterations in less time, and giving a much better resource estimation for each line of code. One new feature that optimizes the platform architecture are host channels. These allow memory transfers from the host to the accelerator to be overlapped with kernel execution to significantly reduce latency between host and accelerator data movement. Also, reference platforms for the production Silicon ARIA 10 and the ARIA 10 SoC dev kits are available, as well as the board support package for the Intel Xeon and ARIA 10 FPGA device. we are releasing a new library for neural networking IP demo implementation of AlexNet, performing classification and scoring. This shows how to build optimized topologies on the FPGA for neural networks. It can be used as is or modified to build a custom topology or customized specifically to something like GoogleNet. There is a tool that is available that leverages the predictive nature of our implementation to allow for architectural exploration and quickly provide performance estimations and targets for that implementation. We are also releasing an SGM reference design that demonstrates how to build solid array architectures very efficiently in the FPGA, in this case performing matrix multiplies. And this implementation is capable of 970 gigaflops on our ARIA 10 device. I wanted to say thank you, and I hope you found this very quick summary of the new features in Altera's SDK for OpenCL version 16.0 useful and helpful. But as always, refer to the documentation for a complete list of all the new features. My name is Bill Jenkins, and I'm a Senior Product Specialist in the Marketing Department at Altera, now part of Intel. I wanted to spend a few minutes just to talk to you about some of the differences between FPGAs and general-purpose GPUs being used as accelerators. Let's take a step back and first explain what industry trends are leading towards the requirement for accelerators. The types and complexity of processing is continuing to increase, and the amount of data being processed as well as the pipelines to move that data around is increasing rapidly. So there's an inherent struggle to scale systems up to meet these increasing demands without a massive increase in cost, power, or system size. Without the use of power-efficient acceleration, the power consumption and cost of the thermal dissipation is often the limiting factor in scaling these systems up. Then there is the complexity of managing the synchronization of data throughout the system using such things as MPI, a massive passing interface, which is rendering high-performance computing intractable. So one answer to the scalability problem is to introduce a more power-efficient accelerator to offload the processor of specific tasks. Whether it's the Xeon Phi, general-purpose GPU, or an FPGA, there are varying options that allow users to tailor the solution for the problem. So let's first discuss the general-purpose GPU. They are highly data-parallel fixed architectures. They allow a single instruction to operate on multiple bits of data, what we call SIMD, in parallel. Applications with high ratio of arithmetic operations to memory operations are ideal. The GPU is actually being leveraged to perform non-traditional graphics applications, but rather general-purpose acceleration or application function processing. Much more power-efficient than distributed computing on multiple CPUs by far. But they have GDDR memory, which is very high bandwidth, but also one of the leading drawbacks for power consumption of the GPU. It also has limited ingress and egress methods, while PCI Express and NVLink and even direct link to network cards are becoming more prominent, still very minimal solutions. Also, task parallelism computations are not handled well on GPUs, and they do require low-level programming to get the high performance out of them. But on top of that, they have very short life cycles, with new generations of chips coming out more frequently, requiring different modifications to the code to re-optimize for that new architecture. Now let's go over the FPGA a little bit as well. Also, highly parallel but customizable architectures, and they very well support either data or task parallel applications. They're used in a variety of applications, including data, signal, or image processing. They're effectively customized hardware for the specific problems you're trying to solve. The resulting architecture can remove the dependencies on high-speed and power-hungry external memory and caching. It supports hundreds of standard interfaces for ingress and egress, whether PCI Express, Ethernet, Serial Rapid I/O, Interlac, but it also, because it can get data into all these different methods, it allows inline processing directly from the data interface without moving data back and forth from the hooks. These architectures provide optimal power efficiency, typically about a fifth that of a GPU. There's also a low-level programming language required to get high performance out of the FPGA, and we actually offer both hardware or software development flows. But the key difference is, when you write that code, you write it one time, and you can take advantage of all the benefits of the next generation architectures without having to go back and modify your code. But the devices also last for 15 years before you need to go to that next architecture. So because a lot of people may not actually know what FPGAs are, let's spend a second just to explain why FPGAs are so power efficient. FPGAs are fine-grained, massively parallel architectures that contain building blocks to create extremely power-efficient solutions. They consist of millions of reconfigurable logic elements, memory blocks, thousands of variable precision DSP blocks, dozens of high-speed transceivers, as well as multiple high-speed configurable memory controllers, and even ARM cores. So if we were to take a look at the inside of that FPGA, zooming in on those details a little bit more, here's what we'd find. The first thing you'd see are the basic building blocks of the FPGA, which are, at its simplest form, are elements that perform single-bit operations such as addition, subtraction, or NOR/NOT logical operations in a single register to store the results. These basic elements are surrounded with a flexible interconnect that allows the connection of these elements together, as well as to other internal resources. This allows building custom operations by configuring and interconnecting these basic elements together. Simple examples such as a 16-bit adder, a 32-bit square root function, or a custom 64-bit shuffle and encoding function. In the FPGA, there are megabytes of internal memory that can be configured and grouped together using the interconnect to create various cache architectures or memory storage structures. These can also be configured and grouped together to create lots of small caches or fewer larger caches with different depths and widths. There are also dedicated variable precision DSP blocks in the FPGA that can be used to perform a variety of floating point operations such as multiplies and accumulators. The configurable interconnect allows all these building blocks to be connected to build a custom data path that explicitly matches your application based on the code you wrote. In addition, the custom data path can be connected directly to the custom or standard I/O interface to bring the data in and out of the FPGA and perform inline data processing. Let's now take a look at how that custom data path maps to the software world and the advantages that the FPGA can bring. Here we have a simple instruction that multiplies the value stored at a memory location by a constant value of 42 before adding it to the value stored in another memory location and updating it. When we break this high-level instruction down into CPU instructions, you can see that to multiply and addition before finally storing the result. Fairly straightforward. If we look at a simplified view of a CPU, and we look at just one of the 6 CPU instructions we saw in the last slide, we're looking at running value into a register, we can see how much of the instruction path is not being used. This is a very inefficient use of the hardware. In many cases, CPUs and GPUs can run as low as 5 to 10% efficient use of the hardware. What we get from our compiler when targeting an FPGA is a custom data path that matches the instructions you've written exactly. Remember, the high-level instruction we wanted to execute, the resulting implementation in the FPGA would look like this block diagram reflected here. We are effectively building exactly what you need, the exact operations, the exact data widths, and the exact memory size and configuration to get the optimal throughput latency at the minimal amount of power. A much more efficient use of the hardware. You can also imagine that if this instruction was in a loop, the efficiency would grow even more, and this would ultimately be creating a pipeline parallelism, which where FPGA really shines. Let's start to compare and contrast some of the specifics between FPGAs and GPUs. One such area of differentiation is in the way the data is moved. In the GPU, data is typically moved from the host over pieces of express. Instructions and data are constantly sent between the host and the GPU memories. This back and forth memory adds a significant amount of latency, and to overcome that latency requires buffering large amounts of data before sending it to the GPU to be processed. This forces a requirement for very high-speed memory and host memory. Now, in the FPGA, not only is the way they get data into and out of the FPGA 100% customizable and flexible for whatever I/O standard is required, but FPGAs can even leverage the internal interconnects in the FPGA to pass the results from one instruction to the next. This allows algorithms to be architected to leverage the very high-speed interconnect and memory bandwidth of the FPGA and minimize the need to go to external or host memory unless buffering is needed. If it is needed, then optional localized memory buffers can be implemented to allow each kernel to have its own buffer, or they can share buffers. Let's look at how GPUs deal with fine-grained data sharing. Some GPU techniques involve implicit single instruction multiple thread synchronization. So if we were to take a look at something like reduction, based on the number of warps or threads that a GPU can operate in parallel, let's say in this example 16, then for each step or stride, all 16 of those threads have to run concurrently. So when you're doing reduction, only a few of them effectively are looked at each clock cycle.